Welcome to class 12 of the basic electronics. So we were studying the full wave rectifier, and this is a circuit that of full wave rectifier that we were actually studied, and we have two diodes here, D1 and D2. And let me repeat it briefly what we learned the last day. When Vs is actually positive, so the voltage drop across both these coils of the secondary windings are actually Vs. So we have two coils of the secondary winding, and the center is actually ground. Okay, so the voltage drop across each of the secondary windings is actually Vs. Okay, and when Vs is actually positive, this diode D1 is actually forward biased, but this diode D2 is actually reverse biased, because D2 is actually connected, or the P side of D2 is actually connected to the negative voltage here, or the negative pole here. Okay, so D2 is reverse biased, and so current would basically flow along this path. So this is the path of the current flow when Vs is basically positive and D1 is forward biased, and since D2 is actually reverse biased, no current would actually flow through D2. Now when Vs is actually negative, this diode D1 is actually reverse biased, and this diode D2 actually becomes forward biased, because again the P side of D2 is connected to the negative pole here. So when Vs is negative, the positive voltage is actually the positive voltage actually appears at this negative pole. So this makes D2 actually forward biased. Okay, so when Vs is negative, D1 is reverse biased and D2 is forward biased, and so the current basically now flows through this path. Okay, so note that the direction of the current through RL is actually the same, both when Vs is positive and negative. Okay, so the voltage drop across RL, or the voltage that appears across RL, is always positive. And this is basically this green line here, that is these green lines here basically denote the output voltage of the output voltage across the load resistor RL. So we see that the load resistor that appears across RL is positive both during the positive and negative parts of Vs, or both during the positive and negative parts of the cycle for Vs. The output voltage across RL is actually positive. Okay, and since the output voltage is actually positive almost during the entire cycle of the waveform, or almost for the entire cycle of Vs, this circuit is known as a full wave rectifier. Okay, rectifier, because again the output voltage across RL is never negative, so the output voltage across RL is always positive or 0, so it is rectifying the voltage. And full wave, because it is outputting positive voltage almost across the entire cycle of Vs. Okay, both when Vs is positive and negative, the output voltage across RL is positive, so it is rectifying the whole cycle basically, and that is why this is known as a full wave rectifier. And now this is a transformer. As I said the last day, this part is the transformer, and its center is actually, the center of the secondary coil is actually grounded. So this is known as the center tapped transformer. So this is known as a full wave rectifier with center tapped transformer. Okay, now let us look at a few properties of this circuit. So first of all, we need to find out what is the peak inverse voltage required for each diode, because as I said that diodes which has a higher peak inverse voltage, they actually have a higher cost actually. Okay, because uh, the diodes which have a higher peak inverse voltage, this means that the diode would actually go into breakdown regime for a greater reverse bias voltage. It can endure a higher reverse bias voltage without going to the breakdown regime, and these diodes generally have a higher cost. Okay, so this is an important parameter, that what is the requirement of the peak inverse voltage for a rectifier circuit. So we'll be applying Kirchhoff's voltage law in this loop over here to find out the peak inverse voltage of this diodes. So we'll be applying Kirchhoff's voltage law in this loop. Okay. So now let us actually name these points. So this point is named as A here, and then the center point is named as B here, and then we name this point as C, and let us call this point D, and let us call this point E. Okay, now if we apply KVL to this loop, which is circled in green color, we get VCA plus VAD plus VEC equals to 0. Okay, where we are following the notation that Vxy is basically Vx minus Vy. Okay, so this is basically the notation that we are following. This basically means that VEC is equal to minus VAD plus VCA. Okay, now let us consider the positive part of the cycle. As I said that during the positive part of the cycle, or when Vs is basically positive, this diode D1 is forward biased and this diode D2 is reverse biased. So since D1 is forward biased, this voltage across D1 is always approximately constant at V gamma. So VAD is basically V gamma here, and then VCA, which is basically VC minus VA, which is the voltage that appears across the total secondary coil. So this is equal to 2 Vs. Now VEC is basically the voltage across this diode D2. Okay, so when is VEC minimum? VEC is minimum when VS is basically maximum. Okay, so when VS is basically maximum, then VEC would be minimum. So VEC min equals to minus V gamma plus 2 Vs max. So this is the maximum reverse bias voltage or the negative voltage that this diode D2 has to endure. And when we write the peak inverse voltage rating, we do not put this negative sign here because we take the magnitude actually. So the maximum peak inverse voltage that can appear across this diode D2 during reverse bias is basically so we will write this in mod, because as I said that when we write the peak inverse voltage, we take the magnitude of the reverse bias voltage and not exactly the polarity. So this is the magnitude of VEC min, which is V gamma plus 2 Vs max. Okay, so earlier in case of the half wave rectifier, we saw that now VEC is basically the magnitude of the reverse bias voltage that appears across the diode D2, and as I said let us consider the positive part of the cycle of Vs. And just as I said that during the positive part of the cycle for Vs, this diode D1 is actually forward biased and this diode D2 is actually reverse biased. Okay, so since this diode D1 is actually forward biased, the voltage drop across this diode D1 is basically V gamma. Okay, so VCA is basically Vc minus Va, which is minus 2 Vs. VAD is basically Va minus Vd, and as the voltage drop across the diode is V gamma, this VAD is Va minus Vd, and this is equal to plus V gamma here. Okay, and plus VEC is the reverse bias voltage drop across the diode D2, so we just call it VR, R for reverse. Okay, is equal to 0. So the reverse bias voltage VR is basically 2 Vs minus V gamma, and now this reverse bias voltage VR is basically maximum when this quantity Vs is maximum. So VR max is equal to 2 Vs max minus V gamma. Okay, so this is the maximum reverse bias voltage drop across the diode D2, which is basically equal to 2 Vs max minus V gamma. So peak inverse voltage that is required for the diode D2 is equal to 2 Vs max, and Vs max is the amplitude of Vs minus V gamma. Now we have noted that for the half wave rectifier discussed earlier, the peak inverse voltage rating used to be Vs max minus V gamma. Okay, for half wave actually. Okay, so definitely this full wave rectifier actually has a higher, or actually requires a diode, or actually requires diodes with higher peak inverse voltage rating. Okay, this is actually a disadvantage because, as I said earlier, the diodes which have a higher peak inverse voltage rating, or diodes which can actually endure a higher peak inverse voltage, generally has a higher cost. Okay, so this increases the cost of this circuit, or the cost of construction of this circuit. And the second disadvantage is that note that the secondary winding here actually have twice the number of coils than that was earlier required. Okay, so the total number of windings of this secondary coil is basically 2n2. Okay, and so we have n2 number of windings here, and we have another n2 number of windings here. Okay, so this is also a disadvantage because generally when we have a higher number of windings, this actually makes the transformer bulkier, or it increases the weight of the transformer. So these two are basically the disadvantages of this full wave rectifier circuit. So let me document it here. So disadvantage requires diodes with higher PIV rating. So this is point number 1, and point number 2 is needs twice the number of turns or windings in the secondary coil. Okay, now just as we discussed earlier that this is our output waveform of this full wave rectifier, and just as I discussed that this circuit is also known as a center tapped transformer full wave rectifier. So this is the output. This green colored line on this graph here actually denotes the output of our center trap transformer full wave rectifier. Now we don't want this output actually. As I said that at the output we want a DC voltage or a almost constant voltage actually. Okay, we do not want this large variation in output, that it varies from 0 to again Vs minus V gamma and then again 0. We do not want this large variation in the output. At the output we want a voltage which is almost constant. Okay, and just as before, what can we do is we can actually put a capacitor filter in parallel with this resistor RA. Okay, so the function of this capacitor is to charge itself and then discharge when no current is flowing through the diode, so that an almost constant voltage is actually maintained across the load resistor RL. So this is known as a center tapped transformer full wave rectifier with capacitor filter. Okay, so let us draw the output waveform. So this maximum voltage across the load resistor RL in case without the capacitor filter would be Vs max minus V gamma. Now if we draw the output of this center tap transformer full wave rectifier with capacitor filter, we will get a plot like I will show now. So initially when the capacitor is discharged and this circuit is turned on, the capacitor charges up. Okay, it reaches its maximum at this point when Vs is also at its maximum value here, and then when Vs decreases, this capacitor cannot discharge immediately, and so this capacitor maintains this constant voltage, which causes this diode immediately to become reverse biased. Okay, and when it becomes reverse biased, no current can actually flow through this diode, so the capacitor actually discharges itself through this path just as before, and an almost constant voltage across the output is maintained by the capacitor. Okay, and the capacitor would actually discharge a little bit before charging again, and then when it reaches this point here, this capacitor again charges itself. Okay, and so now this diode D2 is actually charging the capacitor at this point here, because D2 is actually turned on, or D2 is actually in the conducting state, so it just charges the capacitor through this path. Okay, so it charges up and then again it discharges itself, and then again here it charges up a little bit and discharges itself just like before actually, and this process basically continues. Okay, so this is the waveform. This black is the waveform with an added capacitor filter. Okay, now note that in this case the capacitor actually charges twice during each cycle. Okay, for the half wave rectifier, the capacitor would actually charge once during each complete cycle. So each complete cycle is basically the total cycle of positive and negative parts up to here. Okay, so in one time period earlier, the capacitor would charge up itself once for the half wave rectifier with capacitor filter. Now for the full wave rectifier with capacitor filter, in one time period, which is basically this window, the capacitor actually charges up twice. Okay, and since the capacitor is charging up twice during each cycle, the time period between successive charging events becomes Tp by 2 instead of Tp. Okay, so let us consider that Tp is basically the time period of the secondary waveform or the time period of Vs. Okay, so here the capacitor charges up twice during each time period Tp. So the time interval between successive charging events is Tp by 2. So earlier for the half wave rectifier with capacitor filter, the time period between successive charging events would actually be Tp. Now the capacitor is charging up twice during each time period, so the time interval between successive charging event is actually Tp by 2. Okay, so the ripple voltage V ripple, which is again the difference between the maximum and minimum output voltage. Okay, Vc max minus Vc min. Okay, so this is equal to Tp by 2 Vc max, approximately equal to divided by RLC, which is equal to Tp Vc max by 2 RLC. Okay, so we note that V ripple has actually reduced. Earlier it was Tp Vc max by RLC, now it is Tp Vc max divided by 2 RLC. So which is obvious because the capacitor is actually charging up twice during each time period. So basically the capacitor is discharging less. Okay, so the capacitor is discharging for a shorter time period. Okay, so since the capacitor is discharging for a shorter time period, the difference between the maximum and minimum voltage across the capacitor also reduces, which results in reduction of this ripple voltage. So this is actually an advantage here, that ripple voltage in a full wave rectifier is actually half or approximately half that of the half wave rectifier. So ripple voltage of a full wave rectifier with capacitor filter is approximately half of that in a half wave rectifier in a with a capacitor filter, with a capacitor filter. Okay, now we saw that for the full wave rectifier with center tap transformer, the peak inverse voltage rating of each diode must be 2 Vs max minus V gamma, which is actually almost double of that of the half wave rectifier. Okay, so and as I stated that this is actually a disadvantage because diodes which have a higher peak inverse voltage rating generally cost higher. So diodes which have a higher peak inverse voltage rating generally can endure higher voltage or higher reverse bias voltage without breaking down, and they generally cost much higher. So this is actually a disadvantage. And another disadvantage is that the full wave rectifier with center tap transformer actually needs twice the number of secondary windings, which makes the transformer bulkier. It makes the circuit heavy basically. Okay, and of course since the winding number is more, the cost is also more basically because you need more metal. Okay, so these two are the advantages of a full wave rectifier with center tap transformer. So the full wave bridge rectifier actually avoids this issue. Okay, so the full wave bridge rectifier actually avoids both of these issues, and again it is a full wave rectifier. So let me draw the circuit here for you to understand. So we have this primary windings Vi here, and we have this secondary windings Vs, and then there is this diode D1 which is connected to this load resistor RL, and then there is this diode D2 over here. So this is D1 and this is D2. Okay, and then we have another diode here which is connected in an opposite fashion to D1. So let us call this D4, and we also have another diode here which is again connected to in an opposite manner to D2. So let us call this diode D3. Okay, now let us consider the time when Vs is basically positive. So when Vs is basically positive, this diode D4 is actually reverse biased. Okay, so no current can flow through D4, but the current the diode D1 is actually forward biased. So current would actually be flowing through this D1 and then through this load resistor RL and then through D2 and into this circuit here. Okay, note that current cannot flow through D3 from this point. Okay, because current cannot flow through DT in the reverse direction. Okay, so current would flow through D1, then through the load resistor RL, and then through D2, and then to the ground. Okay, so this is the direction of flow of current when our Vs is basically positive. So this is the current path when Vs is positive. Now when Vs is basically negative, when Vs is negative, then this point over here is actually the negative voltage, and this point actually has the positive voltage when Vs is negative. So when Vs is negative, the voltage polarity basically reverses itself. So during that time, this diode D3 is actually forward biased, but this diode D2 is actually reverse biased. So no current can flow through D2. So current would basically flow in this path when Vs is negative. So through D3 and then through the load resistor RL and then through this diode D4 and then into the transformer in this direction. So note that in both of these cases, both when Vs is actually positive and negative, the current is flowing through the load resistor RL from the right towards the left. Okay, so when Vs is actually positive, current is flowing through the load resistor in this direction, and when Vs is actually negative, the current is actually flowing through the load resistor RL again in this direction. So current is always flowing through the load resistor RL from the right towards the left. Okay, so this point is positive and this point is negative for the load resistor RL, and so no matter whether Vs is positive or negative, the current is always flowing through the load resistor RL from the right towards the left. So the voltage drop across this load resistor RL is always positive. So this is basically a full wave rectifier, and this rectifier is known as a full wave bridge rectifier or simply a bridge rectifier. So this green colored line is basically the current path when Vs is negative. Okay. Now let us see some properties of this circuit. Particularly, as I stated, that the parameters of important are basically the peak inverse voltage rating. Okay, so to understand the peak inverse voltage rating of this circuit, we actually label these 4 points as A, B, C and D, and we basically apply Kirchhoff's voltage law to this loop, this triangular loop over here. Okay, so we apply Kirchhoff's law to this loop. Okay, now applying KVL, what we get is basically VAC plus VCB plus VBA equals to 0. Okay, now the reverse voltage drop across the diode D4 is basically VR equals to VAB equals to minus VBA equals to VAC plus VCB. Okay, now what is VAC and VCB? Consider the positive part of the cycle for Vs. In that case, this diode D1 is actually forward bias, so the voltage drop across D1 is basically V gamma. So VAC is basically VA minus VC, which is basically equal to V gamma. And what is this quantity VCB? So VCB is the voltage drop across the resistor RL. So note that this voltage Vs during the positive part of the cycle is basically Vs is basically VD1 plus VRL plus VD2 during the positive part of the cycle, because the current basically flows through this path. So the secondary voltage is basically the sum of voltage drop across the diode D1 plus the voltage drop across this resistor RL plus the voltage drop across this diode D2. Okay, so VD1 and VD2 are basically V gamma. So we can write this as V gamma plus VRL plus V gamma. So basically VRL is Vs minus 2 V gamma and VCB is basically VRL equals to Vs minus 2 V gamma. Okay, so here we replace this VCB by Vs minus 2 V gamma. So this is equal to Vs minus V gamma. Now the maximum reverse voltage drop across the diode Vr max is basically Vs max. The maximum reverse voltage drop across the diode occurs when this Vs is basically at the maximum value, because V gamma is essentially a constant. So Vs max minus V gamma. So this implies that the peak inverse voltage rating of the diode must be Vs max minus V gamma. So note that for the center tap transformer full wave rectifier, the PIV was 2 Vs max minus V gamma, but in this case the PIV is basically Vs max minus V gamma. Okay, so it has the advantage of a lower PIV rating. Lower PIV rating than that of a center tapped transformer full wave rectifier. And the second point is that less number of turns in the secondary coil. Okay, and this actually comes with some disadvantages also. The disadvantage is that we actually need 4 diodes instead of 2. So let me write it here. So again, if we buy 4 diodes instead of 2, this is again not only costly, but it also actually increases the size of the circuit because we have to place 4 diodes. And then the maximum voltage across the load resistor is Vs max minus 2 V gamma, which is lower than that of a center tap transformer full wave rectifier. Okay, so if you do not remember or do not understand this quantity, let me show you that we have already derived it in the last page. So we have derived this for this formula or this expression for VRL here, which is Vs minus 2 V gamma, and VRL is basically maximum when Vs is maximum. So the maximum voltage drop across the load resistor RL is Vs max minus 2 V gamma. Just like I wrote it here, Vs max minus 2 V gamma. Okay, similar to the other cases of rectifiers, in this case also we can actually put a capacitor in parallel with the resistor to make it a full wave bridge rectifier with capacitor filter. So I am not discussing it here. It's not difficult to actually analyze that circuit. So if you want, just do it yourself. Okay, so let us now discuss one of the application of the breakdown regime of the diode. And as I said earlier, that a diode doesn't obey the diode equation in the breakdown regime. Okay, so let us discuss an application of the breakdown regime of the diode. Okay. So let me first draw the IV characteristics of the diode. So this horizontal axis is the voltage axis, and this vertical axis is the current axis, and then the current across the diode during the forward bias condition increases in this fashion, and the current across the diode during the reverse bias condition basically is approximately 0. Again, it's slightly difficult to draw here, but and then suddenly the diode actually enters the breakdown regime around here, and the current increases very sharply with the applied voltage. Okay, and as I stated earlier, that the diode actually doesn't obey the Shockley equation or the diode equation in this regime. Okay, so this is basically the breakdown regime of the diode. So let me write it here. This regime is the breakdown regime of the diode. The diode doesn't obey the diode equation or Shockley equation in this regime. So I don't remember if I have told it before, but the diode equation is also known as the Shockley equation actually, because it was derived by someone whose surname was actually Shockley. Okay, and as I mentioned earlier, that one of the difference between this forward bias regime, which is basically this regime in the first quadrant, and the reverse bias regime, which is basically this regime in the third quadrant here, the difference is that here the voltage after which the diode current increases sharply with the bias voltage, which other words is known as the cut-in voltage or V gamma. This voltage lies in the range of 0.3 to 0.8 volts. Okay, on the other hand, the voltage after which the diode current increases sharply with the applied bias in reverse bias condition, which is also known as the breakdown voltage, generally denoted by the letter Vz. So this voltage is actually a few volts. Okay, so so basically this V gamma is actually much lower than Vz. Okay, or this cut-in voltage is actually much lower than the breakdown voltage Vz. And the second difference is that Vz can be actually controlled by appropriate fabrication techniques, but V gamma cannot be controlled. Okay, so Vz can be controlled by appropriate fabrication techniques, but V gamma can't be controlled. For example, in a silicon diode, for the same silicon material, Vz can be actually controlled by increasing or decreasing the doping concentration, and Vz can be actually anywhere from -5 volts to -15 volts, let us say, or even higher. Okay, we can actually control this breakdown voltage Vz by appropriate fabrication techniques. On the other hand, for the silicon diode, this cut-in voltage V gamma doesn't vary much. The standard is V gamma is 0.7 volts for silicon diode, and I mean, by changing the fabrication technique or by other techniques, we can actually change this 0.7 volts to 0.73 volts to 0.75 volts, but it cannot go from 0.7 volts to, let us say, 2 volts. And that is not possible. On the other hand, it is actually possible to make Vz or the breakdown voltage 10 volts instead of 5 volts. Okay, minus 10 volts actually, minus 10 volts instead of minus 5 volts. Okay, so Vz can be controlled by appropriate fabrication techniques, but V gamma cannot be controlled. And the second point is that these characteristics here in the breakdown regime is actually sharper compared to these characteristics in the forward bias regime beyond the cut-in voltage. Okay, so basically, in other words, the slope of this IV graph in the breakdown regime is actually higher than the slope of the IV graph in the forward bias regime beyond the cut-in voltage. Or in other words, in the breakdown regime, the current increases more sharply compared to the forward bias regime beyond the cut-in voltage. Okay, so the breakdown regime has a sharper characteristics compared to the forward biased regime. Of course, the forward biased regime beyond the cut-in voltage, that is. Okay, so these two properties, that the breakdown voltage can be controlled by appropriate fabrication techniques and the current increases very sharply with the applied voltage in the breakdown regime, actually make this breakdown regime of the diode suitable for application in voltage regulation. Okay, so let me just describe what is voltage regulation and how can we construct a voltage regulator with the help of this breakdown regime of the diode. So for voltage regulation, we basically use a special kind of diode which are known as Zener diode. Okay, and Zener diode are basically highly doped PN junction where the breakdown regime depends on quantum tunneling and not on avalanche mechanism. Okay, so let us discuss that how this Zener diode can actually be employed as a voltage regulator, and the symbol of Zener diode is basically like this. So we have this diode here, and then when we draw the diode, we draw this straight line and then this connector over here. So in case of Zener diode, instead of this straight line, we draw a symbol which represents Z. Okay, so Z for Zener. So we draw a Z-like symbol here, and we draw this connecting wire here. So this is basically the symbol of a Zener diode. Okay, so in this graph we have drawn this IV characteristics of the diode in reverse bias situation. Okay, the current doesn't increase much with the applied bias, and then when the diode actually enters this breakdown regime, or the reverse bias voltage across this diode surpasses this breakdown voltage Vz, then the current basically increases sharply with the applied reverse bias. Okay, now let us consider this circuit. We have a DC voltage source over here which is connected to the resistor Ri, and then we have this Zener diode which is attached to Ri and the negative pole of the Vz, and this Zener diode has a breakdown voltage of Vz. Okay, so this is a parameter of the Zener diode, that Vz is the breakdown voltage of the Zener diode. If the voltage increases up to Vz, then this Zener diode would reach the breakdown regime, and we basically take our output voltage from between these 2 points over here, that is across the Zener diode. Okay, the output voltage is the same voltage across the Zener diode. Now let us draw the characteristics of the input output characteristics of this circuit. So here the x-axis is basically V, which is the input voltage or the DC voltage. So this voltage source over here, and the output voltage is V0, that is this voltage over here. So what would be the input versus output characteristics? When V is 0, the output voltage is also 0. So it starts from the origin 0 point, and as this voltage V increases, since this diode is actually reverse biased, for small value of this voltage V, no current would actually flow through this diode. Okay, if no current flows through this diode here, then there is no voltage drop across this resistor Ri. So if there is no voltage drop across this resistor Ri, the entire input voltage actually appears across this Zener diode with breakdown voltage Vz. Okay, so basically the output increases at the same rate as the input. Okay, so the output is basically the same as the input. So if the output increases linearly with the input, of course with a 45-degree slope. Okay, now somewhere here let us consider the breakdown voltage of this Zener diode is somewhere here. So this point let us call it Vz. Okay, so this slope is 45-degree because, as I said, since no current is flowing through this resistor or no current is flowing through this diode, no voltage drop actually appears across this resistor. So the entire input voltage is appearing across this reverse bias Zener diode. Okay, so this output increases with the input with 45-degree slope, and then as soon as the input reaches to the value Vz, this diode, this Zener diode, enters the reverse bias breakdown regime. Okay, and when this diode basically enters the reverse bias breakdown regime, the voltage across the diode cannot change much, because as we see here that even for a large change in the current, the voltage change across the diode is actually negligible. Okay, so once this input voltage reaches the value of Vz, the output across the diode actually becomes constant. Okay, now after this input voltage reaches this value Vz, the output voltage across the diode becomes constant because the diode has now entered the breakdown regime, and current starts to flow through this diode. Okay, and any increase in the input voltage beyond this breakdown voltage Vz actually appears as a potential drop across this resistor. Okay, so beyond this input voltage Vz, or when the input voltage increases beyond the breakdown voltage Vz, the output voltage approximately becomes constant. Okay, so this is basically the input versus output characteristics of this Zener diode. So what is the value of Vri, which is the voltage drop across this resistor? So Vri is basically equal to 0 for V less than Vz, equals to V minus Vz for V greater than equal to Vz. Okay, so this is the value of the voltage drop across the resistor. Okay, now we can actually connect a load resistor RL across this Zener diode to get a regulated output voltage. Okay, so this is a load resistor RL across which we want a regulated output voltage, and we can actually connect this RL across this Zener diode to get a regulated output voltage. For example, if I have a circuit which cannot endure say a voltage which is greater than 5 volts. Okay, if the voltage across the circuit or if the voltage across the chip actually increases to a value greater than 5 volt, then that circuit would become damaged. Okay, so these are the cases where this Zener diode regulator is used, and as we see from the input output characteristics of this Zener diode voltage regulator, okay, the voltage across the diode cannot increase beyond a maximum value of approximately Vz. Okay, and this RL is basically the load resistor across which we basically want the regulated voltage actually, or across which we do not want a voltage which is higher than Vz. Okay, or let us say RL can also be a load resistor where we want an approximately constant voltage. Okay, so if we want a constant voltage across this load resistor RL, then what we do is we choose a voltage V which is actually higher than Vz, and we use this circuit over here to regulate the voltage. So what happens here is, if we use a voltage V which is higher than Vz always, then this voltage V minus Vz actually appears across this resistor Ri, and the voltage across the Zener diode is always approximately Vz, so the voltage across RL is also always approximately Vz. So we get a regulated output voltage, or we get a constant voltage at the output load resistor. Okay. Now you may basically ask the question that what is the necessity of this resistor Ri, or what will happen if I disconnect this Ri, because as far as we can understand that the voltage is regulated by this Zener diode. Okay, this voltage is regulated by this Zener diode and not by this resistance Ri. So what is the function of this resistor Ri? The RL, we can understand that this is the load resistor across which we want a regulated output, but what is the function of this resistor Ri? So we put this resistor Ri here so that it can consume the excess voltage V minus Vz. Okay, if this voltage V increases to a value higher than Vz, then the Zener diode would reach the breakdown regime and the voltage across this Zener diode would approximately be constant at Vz. Then where would this excess voltage V minus Vz go? This excess voltage V minus Vz would drop across this resistor Ri here. Okay, if this resistor is not put here, okay, if we remove this resistor Ri, then what will happen is that, because there is no resistor to actually consume this extra voltage V minus Vz, the Zener diode would actually be forced to suffer a voltage drop of V across it. Okay, that since this resistor Ri is not there, or if we if we short circuit this resistor Ri, what will happen is that there would be no impedance to consume this excess voltage V minus Vz. So the entire voltage would drop across this Zener diode with breakdown voltage Vz, and if all the voltage actually drops across this Zener diode, then the current across the Zener diode would be so high that this would basically burn the Zener diode. Okay, so I repeat again that this excess voltage V minus Vz is actually consumed by this resistor Ri. So this resistor Ri is basically put here to actually limit the maximum current across the Zener diode and to consume the excess voltage V minus Vz. Okay, so that the Zener diode doesn't burn. Okay, so this resistor Ri basically prevents a large excess current from flowing across the Zener diode, and this resistor Ri prevents any voltage beyond Vz to drop across the Zener diode. So this resistor Ri basically protects the Zener diode from destruction. So we'll do some problems to actually clarify this idea that why the resistor Ri is actually put here, but I hope you have got a feeling that why this resistor is required. So this resistor is required to consume this excess voltage V minus Vz when the voltage across when the input voltage actually increases to a value higher than Vz. Okay. Okay. So that's all for today. So the next day we will actually do some problems on Zener diode voltage regulators, and we will do some class of circuit known as clippers and clampers. So let us do up to here today. Thank you everyone.